Hello everyone, welcome to chapter 2. In this chapter, we are going to focus on something much more familiar, the sky above us. You will learn how to read the sky like a user manual, the way sailors and early astronomers once did. And you will discover why the stars move the way they do, and how we measure their brightness, and how Earth's motion causes the patterns we see every day and every year. So, by the end of this chapter, you should be able to answer some very practical questions like how stars and constellations got their names, or why some stars appear brighter than others. You will also understand the daily and yearly motion of the sky and how all this ties into Earth's climate and seasons. It's all connected, and you are going to start seeing those patterns. Here's how we will break it down. First, we will talk about how we name and group stars into constellations. Then, we will explore how the sky moves both daily and over the year, and what that tells us about Earth's motion. We will also look at the sun and planets in our sky and wrap up with how long term astronomical cycles, like Earth's tilt and orbit, influence our climate. Now, let's look up at the night sky, not just with our eyes, but through the lens of history. So, for thousands of years, people around the world named the stars and grouped them into constellations, brightest stars that appear to form groups. Some were based on myths, heroes, or animals, and while some shapes actually look like what they are named for, many don't. And for generations, people used the sky to tell stories, myths, and legends passed down for thousands of years, written in the stars. Why do you think that is? Let's explore how people found meaning in the stars. Imagine being out under the stars with no phones, no lights, no distractions. What patterns would you see? What would you name them? Cultures all over the world gave their own meanings to the stars. So these constellations are ancient star patterns passed down as stories of mythical heroes and monsters. Isn't it fascinating that people around the world look at the same stars but told completely different stories about them? Orion could be a giant, a tiger, or a deer god, all depending on where you lived. And the Big Dipper. Did you know the idea of it being a bear might be over 12,000 years old? That's older than writing. Let's pause. If you had to rename a constellation from your own culture or imagination, what would you call it? A dragon? A taco? Let's play a game of sky real estate. Back in the day, star boundaries were like sketchy doodles, vague, overlapping, and inconsistent. A star like Alperettes was in two constellations at once. But in 1928, astronomers said enough and drew official borders. So now we have 88 constellations, and every star has a permanent home. Now Alpha-Reds is only in Andromeda. So in addition to the 88 official constellations, the sky contains a number of less formally defined groupings. We call them asterisks. So the Big Dipper, for example, is a well-known asterisk that is part of the constellation Ursa Major, which we call as the Great Bear. So here's a challenge. If you had to create your own asterisk using stars from two constellations, what would you name it? Okay, time to break the illusion. So when you look at the Big Dipper in the sky, it looks like those stars are close together. But they are not. They are like pins on a board at different depths, and we are seeing them from just the right angle. That means Constellation might look like the stars are grouped together, but they are not actually close in space. They just happen to line up from our point of view. But some are much farther away and moving in totally different directions. So let's try this. Hold your finger up and close one eye. Now switch eyes. Did your finger jump? That's parallax. And it's how astronomers figure out star distances. So when you look up and see constellations, remember it's a bit like a cosmic optical illusion. In addition to naming group of stars, early astronomers gave individual names to the brightest stars. So have you heard of Betelgeuse? Its name comes from Arabic, means hand of giant. Cool, right? So although the constellations names came from Greek translated into Latin, most individual stars names came from Arabic. But here's the problem. Names like Sirius or Aldebaran don't tell us where the star is or how bright it is. So imagine trying to name every visible star. You would need thousands of names, impossible to remember. So instead of making up thousands of random names, Bayer gave stars a kind of stellar address system. So who is Bayer? He is a German astronomer. So in 1603, Johannes Bayer said, let's get organized and use the Greek alphabet to label stars. So based on their brightness and position in a constellation. If a star's label is early in Greek alphabet, for instance alpha or beta, you can be sure that star is among the brightest stars in that constellation. So to identify a star by its Greek letter designation, you would give the Greek letter followed by the genitive form of the constellation name. For example, Alpha Canis Major is Sirius, the brightest star in Canis Major. So let's try it. If you hear Alpha Orionis, you know it's one of the brightest stars in Orion. If I say Beta Orionis, what do you think that means? It's the second brightest star in Orion. So these names tells us both where the star is and how bright it is. Now can you guess what Beta Centauri would be? It's the second brightest in Centaurus. So Bayer gives stars a systematic name. No more random labels. Let's meet some celebrities of the night sky. These are not just twinkles. Each has its own story. Betelgeuse, for instance, is a bloated orange giant, 500 times the size of our sun. So each is a glowing sphere of gas resembling the sun, with its own unique characteristics. And this figure identifies 8 bright stars that can be considered as famous stars. Can anyone name a star they have heard of? Maybe Sirius? That one is the brightest in the night sky. How about Alpha Centauri? It's only 4.4 light years away and it is the brightest star that is nearest to us. But you have to travel to the latitude of southern Florida to glimpse it above the southern horizon. So ancient astronomers described the brightness of stars using the magnitude scale. Let's go way back over 2000 years. Hipparchus created the first star catalogue and Ptolemy used his ideas. Imagine working on a system people still use today. Impressive, right? So they kept it simple. First class stars were the brightest and sixth class stars were the faintest you could see without a telescope. Kind of like how we rank hotels. First class means top tier. Now here's the twist. It's backward from what you would expect. A bigger number means a fainter star. So if I say a star is magnitude 6, is it brighter or dim? That's right, it's dim. Now we are even more precise. We now use instruments that measure brightness down to decimal places, giving us way more precision. So the magnitude scale is no longer just an estimate. It's a mathematical scale where a lower number means a brighter star. It's even possible to go below 1. Take Chorus for example, not just a cool name, but its brightness is measured as magnitude 3.34. That tells us it's moderately bright, but not a standout. Then there's Vega, famously bright, with a magnitude of just 0.03. That's nearly as bright as it gets in this system. Now, what do you think happens when a star is brighter than first class? Yep, it gets a negative magnitude. For example, Sirius, the brightest star in our sky. It has a magnitude of negative 1.46, and that minus sign means it's really bright. Kind of weird, right? Now, here's a fun fact: if your eyes are super sharp, the faintest you can see is around magnitude 6. But with a telescope, we can go way beyond than that. The keyword here is apparent. This scale doesn't tell us how much light a star actually gives off, only how bright it looks from Earth. And see that little subscript in MV. That stands for visual, because we are only talking about the light our eyes can see, not X-rays or infrared or gamma rays. So when we look at a star, how bright it seems depends on your eyes and even our brain's perception. But science needs objectivity. So instead of asking how bright does it look, we ask how much light energy actually reaches us. That's where flux come in. So flux is a measurable quantity. It's how much light hits 1 square meter every second from a star. Now here's the cool part. Astronomers don't have to guess how bright one star is compared to another. They use a simple mathematical formula that relates magnitudes to flux. So this helps us move from subjective brightness to objective, measurable light energy. So it says if the two stars have fluxes Fa and Fb, then the ratio of their fluxes, which is Fa over Fb, is equal to 2.51 raised to the power of the magnitude difference Mb minus Ma. So Mb is the magnitude of star B, Ma is the magnitude of star A. So what does this mean? For example, if two stars differing in brightness by 5 magnitudes, then it has a flux ratio of exactly 100, which is 2.51 raised to the power 5, which is close to 100. And if it is just 1 magnitude brighter, that is about 2.51 times more flux. So this scale is logarithmic, not linear. And we can also go the other way. If you know the flux ratio of two stars and want to find the magnitude difference, it is convenient to rearrange the equation into this formula. Here, log means logarithmic to the base 10. Now let's do some examples for your understanding. If the magnitude difference between two stars is 6.32, what is the flux ratio? So now you know the magnitude difference, which is Mb minus Ma. That is the magnitude difference between two stars, and it is equal to 6.32. Now you are asked to find the flux ratio, which is Fa over Fb. So if you plug into this formula, you get that flux ratio must be 2.51 to the power of 6.32. So you will get the answer 336. So that means the star A is about 336 times bigger than the star B. meaning that the flux received on Earth from star A is 336 times greater than that from star B. So let's try another. If I tell you that Sirius shines 24.2 times brighter or has 24.2 times as much flux than Polaris, then what is their magnitude difference? So now you are asked to find the magnitude difference, which is MB minus MA, right? And you have been given the flux ratio, which is 24.2. So the flux ratio is FA over FB, which is equal to 24.2. So you can use this formula and then plug in the numerical value for FA over FB, which is 24.2. And if you get this logarithmic value, you should get the answer 3.46 magnitude. So that means Sirius is 3.46 magnitudes brighter than Polaris. Now that we have explored stars and constellations, including how they are named, the naming systems, and how we measure their brightness with the apparent magnitude scale and flux, let's shift our focus. So understanding individual stars is important, but to really grasp the bigger picture, we also need to look at how the sky itself changes and moves. So in the next section, we will dive into sky and celestial motions, how the stars appears to move across the sky, and what these patterns tells us about Earth's place in the universe.